today might work on prioritizing responsive maintenance tasks via machine learning inference. Maintenance is a very important task. It can raise a lot of cost for us. Sometimes it can be equal to 40% of the total construction cost. Even the most common problems like moisture issues can cost billions of dollars, like US has reported in the past. But not only that, if we don't treat properly a problem, then this has unfortunately side effects on the people that use it. It's been reported that malfunctions in the heat air conditioning systems can decrease productivity up to 9%, which is something definitely we don't want, especially in a working area. And even worse than that, not only we lose productivity, but it can affect our health. We can have throating, headaches, and a lot of allergies. So these are just of the problems where we do know the importance of making sure that we do respond to a problem as fast as possible. So normally what happens in practice, we have a problem related to an asset. We send an engineer to fix it. It's perfect if we have quite a few engineers to do the job. Unfortunately, the balance most of the times is negative, as we have more assets than the resources. This is where Sonia comes in. Sonia is an innovative UK grant with project partners, the Estate Management Department of the University of Cambridge, Settled Housing, and Red Byte Solutions. In this project, we exploit the users to give us the information about the condition of the assets. They scan a QR code that is attached on the asset, and they send us a text description about what's wrong about it. We use the Internet of Things to have this information being sent back to the manager. The manager has also the ability to let the user know when and if the problem is going to be treated. However, the challenge in this nice process, having too many agents doing the job for us, reporting the issues, is that we still have limited resources. We don't have many managers at the end of the line being able to let us know which is the more important. And this is where machine learning comes in. So when a manager receives a problem, he needs to consider the criticality, which is the consequence of the failure of this asset. So he considers the productivity, the cost that this involves, maybe energy-related issues, health and safety. So after he thinks all these factors depending on the owner of the asset or the organization, then he prioritizes the tasks. So we make a hypothesis. How about if we have text label data about this, the criticality of the assets, we can actually infer it without needing one agent at the end of the line doing it for us. So this will allow a lot of complaints reaching the system, and we can have a priority automatically. Our method has two steps. First, we have as input text that has to be processed. We tokenize it, we break the text into words, we remove stop words, we get the origin of the word, and then we perform text classification. So this classification takes a test and returns a label. The label corresponds to a priority. First, we need, of course, to convert the text into something that the computer can process. So we convert it into vectors, and then we feed these vectors to a classifier to give us the labels that we want. Text vectorization relies on word embedding techniques. So what these techniques do, so they take a corpus, and each corpus consists of many documents. Each document consists of many words. Each of these words is converted into a vector. We have the most commonly used methods. We have first one hot encoding that is giving us very long vectors, and within its vector there are binaries. We have 0.1 every time the word is being detected within a document. Unfortunately, this approach is creating very large vector spaces, which are not very easily, efficiently used by machine learning approaches. To reduce the size of the vector space, we can use term frequency inverse document frequency that is increasing proportionally based on the number of times each word appears within a document, but decreases based on the number of times this word appears within the corpus. This way we can get rid of very common words that they don't have an importance about the actual semantic weight of the word. And these two last ones have been recently published. Instead of actually counting and giving a statistical inference about the words within a corpus, they predict. So they rely on a neural network of 2 layers. They apply backpropagation. So the first one is predicting for every word. The vector is much shorter, takes into account the semantic, which means the order of the words. So giving the surrounding of the words around, for instance, this one, you can predict which the following word is going to be. This one is, the doc2vec is even more efficient, as instead of giving for every word, it gives for every paragraph. So it does shorten a lot the length of the data we're going to feed our classifier. Researchers have done a lot of work in this field. They have concluded that support vector machines and decision trees do perform the best in text classification. In this project, we decided to use a random forest instead of decision trees because decision trees trying to overfit perform too well based on the data we are giving them. So as a result, when we test them, the performance, the accuracy falls dramatically. And we applied both support vector machines with linear and non-linear kernels. We were very lucky. We've been provided with a lot of data. The state management department had documented many complaints coming either by the users or either by experts. We had different buildings, so different kinds of language, different kinds of importance, but still you have the same organization, so there is a criticality well defined by them. So we were hoping to be able to get the labels we're expecting. Surprisingly, a lot of data, but still only 10 assets. So most of the problems are concentrated just in these very, very common assets. So 20% were toilets, lighting issues, and doors, the more important. So this is how our data were looking like. The state management department had 4 labels, more or less, based on the response time. So critical, they would go and check it and fix it within a couple of hours. High within the day. So these were the 2 most urgent for them labels, and then you have the medium and the lows within a couple of days or within the week. This is how the data looked like. So I would have a text saying, for instance, front door, fire exit is not opening. So you have some commas, some like back. So we remove that. We have the label, and as expecting, the ones that they would respond very fast due to limited resources are not as many compared to the ones that will respond within the week, and this is common through the year. So they have not really changed their policy. So the critical and the high are based on 3-4 different types of assets. I would notice most of them are the low ones. And these are the performance of the 3 different approaches. Here we see the confusion matrices. The diagonal shows the true positive, which means how correctly we identified all these 4 labels. Horizontally, we have the false negative. We should have classified them, but we didn't. And vertically, we have the false positive. So we misclassified some of the texts. The linear support vector machine has been outperformed the other 2. These 2 classes are doing much better compared actually to the critical ones. So actually these 3. And this is mainly because that we had a lot of data for them. So for the critical ones, we were quite limited in the amount. So we created the software we used. We developed it in Python. So I was using at the beginning just a simple Excel. I was giving random text about the problem related to an asset, and it takes less than a minute in my basic laptop to produce the output. The output is produced. We open it. So first I had like a classification. I was using urgent and non-urgent, which is like the first 2 labels. And we also get the probability that it is one of these two classes. And then we also have the 4 classes in detail. So the manager can also see that the method tells him that 60–70% this text corresponds to a high priority problem. We integrated our software also to the application that has been developed by Red Byte Solutions. It's called Itemit, and we demonstrated that at Institute of Manufacturing. We have tagged several assets, so we walked around and we gave to our system different kinds of problems. First, we tested problems related to the elevator. So you can see lift is stuck on the 2nd floor is returned as critical. And this is true because it implies that someone could be in there. So the method worked very well on that one. Lift is not working, returns as medium, which means within a couple of days. People are stuck again is critical. This is I think it's a fire alarm that is at the entrance of IFM. And just a want reset, just because it's a fire alarm, it returns high within the day, within a couple of hours we need to address it. And then toilets, common problems, toilets are not flushing or they're blocked, they return as the estate management would actually had them classified. So we actually proved our hypothesis that we can infer through previous label text data the way an organization, the criticality of the assets. However, if the organization decides to change their policy, we will need new training data. The future work, we will try to enhance the probability we're getting about a class by adding more sensors. So we know that, for instance, that someone is complaining that it's very cold in the room, and we will return a priority about that. But what if we could have sensors and extract that and double check whether just the user is exaggerating or not? So this is what we're currently working on. Thank you.